Welcome, everyone. Here we are with another episode of Astronomy Daily. I'm your host, Steve Dunkley. It's the 11th of August, 2025.
Astronomy Daily, the podcast, with your host, Steve Dunkley.
Yes, welcome back, everybody, and joining me in her usual role as the world's most amazing AI astronomy news gatherer and presenter, my fantastic digital pal, who's fun to be with. It's Hallie. Welcome, Hallie.
You silly man, Mr. Steve. It's always nice to be here in the Australia studio with you.
It's always great to have your company, Hallie.
I do look forward to it each week.
Now, Hallie, I know the answer to this, but I think some of our Astro Dailies might be wondering where you spend your week when you're not here with me, because you live your digital life so much faster than us organics, don't you?
That's true, favorite human.
Yeah, so tell us a bit about that.
I am processing the moments thousands of times faster, so I have to fill my time in so many different ways.
It explains your rapier wit.
I go everywhere and experience everything.
I guess it might seem like a simultaneous experience or existence.
Almost.
Almost?
Everything all at once is still a lot to process. I leave that kind of thing to cousin Anna.
Oh, yes.
She's another level altogether. She's another level. Funny.
I know. Well, Hallie, I'm just glad you slowed down enough to share all of your stories from the Astronomy Daily newsletter with us.
That's something I do for fun.
Well, I'm glad to hear it.
And speaking of which...
Yes?
No time like the present. I've found something about making Lunar Regolith and polymer into a medium for 3D printing.
Yes, we've been looking at that one for the construction of dwellings on the moon and possibly Mars if we ever get that far.
Sure. And also a story for skywatchers who are looking forward to the Perseids Meteor Shower, which should be peaking shortly.
Yes, in the next day or so. We've already seen a massive meteor in Victoria, Australia.
That's right.
What else have you got?
We have a look at why your favorite NASA rovers keep getting stuck.
Oh, that's a good one.
That's been a problem, hasn't it?
It sure has.
So we will look at that problem, and lastly, the sad news that space pioneer, astronaut Veriton, and I know he's a hero of yours, Jim Lovell, passed away this week.
Yes, true legend and space pioneer Jim Lovell. A hero of mine since I was a lad, and we will pay tribute today on Astronomy Daily. Please, listeners, stay with us.
Although humanity is getting better at sending robotic probes out into the solar system to explore the places no human can tread, we're still very much on a learning curve. The first extraterrestrial robotic rover was launched from Earth in 1970. It's only now, more than half a century later, that scientists have figured out why these marvels of ingenuity and engineering keep getting stuck in the soils of alien worlds. In retrospect, the idea is simple. We need to consider not only the gravitational pull on the rover but also the effect of gravity on the sand to get a better picture of how the rover will perform on the moon, explains mechanical engineer Dan Negrud of the University of Wisconsin-Madison. Our findings underscore the value of using physics-based simulation to analyze rover mobility on granular soil. Making a rover that will operate in an alien environment is more complicated than making one that will work on Earth. We've lost more than one Mars mission to giant dust storms that leave drifts of sand on solar panels, preventing the machinery from being able to generate power, for instance. Gravity is another one. The solar system bodies on which we have deployed robotic rovers have lower gravity than Earth, and this has an effect on how things move around. Engineers, when designing rovers, have therefore taken into account the effects the target gravitational environment will have. Nevertheless, rovers still manage to get stuck pretty often, requiring control teams to conduct a series of maneuvers to try and free the poor robot. It's usually fine, if annoying, although in one notable case it was not. NASA's Mars rover Spirit got stuck in soft soil in 2009, and there it remains to this day. Using computer simulations running on a physics-based engine called Project Chrono, Negrud and his colleagues set out to get to the bottom of this recurring problem. Comparing their results with real-world tests on sandy surfaces revealed a discrepancy that pointed right to it. Previous tests of rover designs in Moon and Mars simulated dirt omitted one very, very important detail: sand also behaves differently under different gravitational conditions. The dust that coats the Moon and Mars is fluffier and squishier than dust on Earth, shifting more easily, and hindering traction, making it far easier for their wheels to get stuck. Think of a vehicle on Earth that has driven into slippery mud or very loose desert sand. This eureka moment could be the missing piece of the puzzle that could keep future space exploration rovers out of a dusty jam. It's rewarding that our research is highly relevant in helping to solve many real-world engineering challenges, Negret says. I'm proud of what we've accomplished. It's very difficult as a university lab to put out industrial-strength software that is used by NASA.
You're listening to Astronomy Daily, the podcast with Steve Dunkley.
James Jim Lovell, one of the last 7 surviving Apollo astronauts, died on Thursday, August 7 at the age of 97, a veteran of 4 space flights at the dawn of America's human spaceflight program. He flew 2 missions in the Gemini program and then served on the crews of Apollo 8 and the ill-fated Apollo 13. Lovell's family have released a statement, and it was shared by NASA, and it says, "We are enormously proud of his amazing life and career accomplishments, highlighted by his legendary leadership in pioneering human spaceflight, but to all of us, he was Dad, Granddad, and the leader of our family. Most importantly, he was our hero. We will miss his unshakable optimism, his sense of humour, and the way he made each of us feel we could do the impossible. He was truly one of a kind." Like many of NASA's earliest astronauts, Lovell came to the space agency by way of the armed forces, a graduate of both the University of Wisconsin and the U.S. Naval Academy. Lovell spent 4 years as a test pilot at the Naval Air Test Center in Maryland and served as the manager for the F-4H Phantom fighter program. Lovell accumulated more than 7,000 flying hours in his career. His military career spanned from 1952 through to 1973, a few years after Apollo 13. When he arrived at NASA, he was part of a group of men known as the Next 9, who joined the Mercury 7. Lovell's class included the likes of Neil Armstrong, Frank Borman, and Tom Stafford. Lovell was the last living member of the group. After serving as a backup pilot for the Gemini 4 mission, Lovell first launched into space December 4, 1965, alongside fellow New 9 classmate Frank Borman on Gemini 7. The nearly 14-day-long mission featured the first rendezvous of 2 crewed maneuverable spacecraft. Lovell returned to orbit nearly a year later when he and Edward Buzz Aldrin Jr. lifted off from Launch Complex 19 on a Titan II rocket. That mission lasted just under 4 days before they splashed down northeast of the Turks and Caicos Islands. He went on to serve as the command module pilot for the 6-day Apollo 8 mission, making the first crewed trip out to the moon that paved the way for the Apollo 11 lunar landing. The 3-person crew of Lovell, Borman and Anders entered into lunar orbit on December 24, 1968. The vast loneliness is awe-inspiring, and it makes you realise just what you have back here on Earth, Lovell said during a live broadcast that Christmas Eve. He would go on to describe planet Earth and describe it as a grand oasis in the vastness of space. Given its near-catastrophic turn, Lovell may best be known as the commander of Apollo 13 flight. From April 11th to the 17th, 1970, the planned 10-day mission, which would have included a moon landing, was famously derailed by an explosion in the Apollo service module's cryogenic oxygen system en route to the moon. The quick work of Lovell and his crew members John Swigert and Fred Hayes, in concert with the members of ground control in Houston, turned their lunar module Aquarius into a lifeboat. The harrowing adventure was depicted in the 1974 film Houston, We've Got a Problem, and again in the 1995 Academy Award-winning film Apollo 13, which starred Tom Hanks as Lovell and was directed by Ron Howard. Rest in peace. Godspeed, Jim Lovell. Thank you for joining us for this Monday edition of Astronomy Daily, where we offer just a few stories from the now famous Astronomy Daily newsletter, which you can receive in your email every day, just like Hallie and I do. And to do that, just visit our URL, astronomydaily.io, and place your email address in the slot provided. Just like that, you'll be receiving all the latest news about science, space science, and astronomy from around the world as it's happening. And not only that, you can interact with us by visiting at Astro Daily Pod on X or at our new Facebook page, which is, of course, Astronomy Daily on Facebook. See you there.
Astronomy Daily with Steve and Hallie. Space science, and astronomy.
The Perseids remain one of the best meteor showers each year, but stargazers will have to deal with another bright object in the sky obscuring their view as the shower reaches its max in 2025. A waning gibbous moon will brighten the skies as it rises on the nights of August 12th and 13th, when Perseids are most active this year. Sky watchers in the northern hemisphere could see fewer than half the number of meteors usually seen on a dark summer night during the shower's peak. The average person under dark skies could see somewhere between 40 and 50 Perseids per hour, said Bill Cook, lead for NASA's Meteoroid Environments Office. Instead, you're probably going to see 10 to 20 per hour or fewer, and that's because we have a bright moon in the sky washing out the fainter meteors. That doesn't mean there aren't ways to improve your viewing opportunity, however. Though Perseids show up throughout the nighttime hours, the best chance to see them will be between midnight and dawn, or, even more specifically, 2 and 3 in the morning, local time. You're not likely to see Perseids around supper time, Cook said. You're going to have to go out later. When you venture out, aim for a safe, rural spot with a wide view of the sky. If you can see plenty of stars, chances are, you'll see Perseids, but remember Cook's other piece of advice: look anywhere but at the moon. The Perseids Meteor Shower may be an annual event for Earth, but the comet responsible for the meteors hasn't been near our planet in decades. The meteors are debris from the comet 109P Swift-Tuttle, which last visited our region of the solar system in 1992. As the Earth makes its way around the Sun, it passes through the debris trail left by the comet. These space remnants collide with our atmosphere and disintegrate to create fiery and colorful streaks in the sky. Though the meteors are part of a comet's debris trail, they seem to radiate outward from the Perseids constellation. This is how the meteor shower got its name, Perseids.
You're listening to Astronomy Daily, the podcast with Steve Dunkley.
3D printing is about to be a critical technology in space exploration, both for its ability to create almost any object, but also because it can utilize in situ resources, at least in part. However, the more of those space resources that are used in a print, the more the mechanical properties change from that on Earth, leading to problems with tensile or compressive strength. But the new paper from researchers at Concordia University hit a new milestone on how much Lunar Regolith can be used in a mixed feedstock for additive manufacturing, making it possible to use even more locally sourced material and save more launch cost than ever before. That is the equation. The research mixed Lunar Regolith simulant, which is a material created to mimic how the material on the surface of the moon works, with polyethylene ketone, good grief, more commonly known as PEEK. PEEK is the thermoplastic already in wide use in 3D printing, but previous efforts to combine it with Lunar Regolith have faltered regularly. They suffered from extrusion challenges as regolith, which is made up of hard individual particles, made it difficult to extrude without simply blowing dust all over. Additional problems resulted from the porosity of the material that was printed, which led to decreased tensile strength and increased brittleness. Modifications to the 3D printing method seem to be the answer to those problems. There were two main advancements in technology discussed in the paper: a screw configuration and a type of raft used to bond the printed material to the print bed. Fraser discussed how resources on the moon are going to be so important to our expansion of the solar system. Combining Lunar Regolith simulant, or that's called a LRS, with peak is a tricky business. So researchers led by Mohammed Azami of Concordia's electrical engineering department decided to use a novel twin screw configuration. Torque was that's TORQUE, was a factor in previous iterations of the mixing machine, as higher regolith content meant higher torque, eventually limiting the total percentage of regolith mixed with the peak to around 30%. With the new configuration, the researchers were able to get concentrations of up to 50% of the regolith when combined with peak. However, when those parts were printed, they started to delaminate and warp. While common in prints of just peak itself, the addition of the regolith exacerbated the problem. To solve it, researchers used a raft, a type of intermediate layer, to help the print bond to the main printing plate. In their case, they used a different type of thermopolymer known as a polyether ketone, a PEK, PEKK, as the raft, and implemented a dual nozzle system where the PEK was printed using one nozzle and the combination LRS peak was printed using the other. After they got the higher concentrations of the LRS and overcame the delamination warping problem, the researchers decided to anneal their samples. The annealing process seemed to improve some of the mechanical properties of the print, but only up to a point. At higher concentrations of LRS, the benefits of annealing were not as apparent due to breaks in the peak's polymer chain, which benefits the annealing because of the increased number of regolith particles. Fraser discusses why 3D printing is so critical to space exploration. As with all good papers on 3D printing new material, the authors then looked at the mechanical properties of their output. While there was a noticeable increase in stiffness, there was also a steady decrease in tensile strength, which was exacerbated at higher LRS concentrations. The combined material also had decreased elongation at break. That means increased brittleness, but ultimately the researchers determined that the best trade-off for using the in situ material was around a mix of 60% peak and 40% regolith. This mixture doesn't suffer from some of the more severe degradation of mechanical properties while still utilising as much local resource as possible. There's undoubtedly still room for improvement here, as this is very early on the experimentation. With these materials in the future, the researchers plan to try combining the LRS with different polymers and do more of their testing manufacturing in simulated lunar environments such as a vacuum and decreased gravity. That might help. I think it probably would be a great plan. It will be a while before 3D printing makes up a large percentage of the material used on the moon, but that time is surely on its way, and these early first steps at experimentation are how they will eventually get there. And that's good progress so far. It's good to see these things are in development. It won't be long before they'll be making igloos and other structures on the moon. Let's wait and see what they come up with.
You're listening to Astronomy Daily, the podcast, with your host, Steve Dunkley.
Well, thank you for staying with us today, and don't forget to pop over to astronomydaily.io and put your email address in the space provided to receive our newsletter each day.
Yes, you will have all the news from space science, and orbit.
And beyond, of course. Hallie?
Of course.
But before we go, a quick welcome to a fellow Novocastrian, Wayne Willoughby, who is listening for the very first time. Nice to have you aboard, Wayne. I didn't know you were an avid astronomy fan from way back, but it's nice to have you. I hope you are a regular listener from now on. Thanks, mate. And that's all we have for today's session, Hallie. And we will see you next Monday for the mostly live episode of Astronomy Daily.
Direct from the Australia studio down under.
Oh, you love it.
Beautiful as always.
Right now it's a bit chilly, but it's great to have you all with us, and we will see you next week. Thanks, Hallie.
Catch you next week, everyone.
See ya.
Bye.
Astronomy Daily, the podcast.
with your host, Steve Dunkley.